Hey guys, welcome to Digital Srini channel on YouTube, and if you haven't already done so, please go ahead and subscribe to this channel, and of course like any videos that you think are very informative for you. Okay, in this video I'm going to talk about satellite image segmentation, and again we have done this in the last video, but the one from last video we loaded the entire data set into memory. But quite often you may find yourself in a situation where you have tens of thousands of images and maybe hundreds of large images that you break down into tens of thousands of smaller images, and then you need to read them directly from the disk, train a model, and segment larger images. So the goal here is to start with larger images, find a way we can organize those, meaning crop them and organize them, so we can use UNet and data augmentation, image data generator from Keras, okay, to read these images directly from the disk, train a model, save the model, and then apply to large images, patch by patch, build them together, put them together, and blend them in a smooth way. So the end result is going to be a smoothly blended segmented image. That's the plan. Okay, if this sounds interesting, please continue this video. Okay, just want to make sure you know ahead of time what the plan is. So the data set, here are a few images that you see on the screen that we are going to use as part of our data set, and this is not an easy task. Actually, it's possible, but not an easy task. And sometimes I find that some of the annotations can be better. Okay, but again we'll learn that as we go along. And there's a bit of information about the data set. Again, this is from landcover.ai. Again, there seems to be quite a few, like a lot of different types of data sets out there, so it shouldn't matter. The process should be very similar. Yeah, if you follow the process that I'm going to show in this tutorial, it should be very similar no matter what data set you work with. But in this specific data set, there are quite a few images, which we'll see in a minute, but there are 4 classes. The biggest class is unlabeled background, where they haven't labeled anything, right? It could contain some features, but that's just completely unlabeled. And then you have buildings. As you can see, there is like a building right there, one right there. So there are buildings, there are woodlands, like wherever you have trees, that's labeled, and water. Okay, I don't have an example here. Water is class number 3. Now, when you look at these images, like here, this image only has 2 regions. One is unlabeled, the other one is woodlands. Woodlands has a pixel value of 2. Yeah, these are pixel values, by the way. Pixel value 0 is unlabeled, 1, 2, and 3. Okay, so if you only have 2 classes, when you plot it using Matplotlib, you are going to see black and white. And the white is the high end of the spectrum of this histogram, black is on the low end, right? But this white is probably different than that. In this example, this is the same because they both are woodlands. But keep in mind that don't make any decisions based on how the masks look like on the screen. Use image J, for example, to open the masks and investigate the pixel values. Okay. So this is a little bit about the data set, and I just want to give you a quick preview of the results that I got. Maybe you can experiment a bit more and you can get better results, but the model converged very well, and the intersection over union for all the classes combined, I was getting 75 to about 80% after training for, I think, like 50 epochs or so. So it's not bad. And here are some examples. Again, like I said, don't judge too much based on the colors. This is exactly what I mean. You see, these two are in a different color. This one is showing up in yellow, but my prediction failed to predict this additional class, which I don't even see here. Yeah, I don't even know why that thing exists. Maybe that edge of that woodland, whatever. Since it did not detect that, it kind of automatically adjusted the range to show the houses in yellow. But just look at the locations, not the color right now. Okay, and this one looks very good right there, and this seems to be doing a pretty good job, although I don't know what that dot is supposed to be. Well, this is the segmented, and in fact my model is actually picking up the tree right here, whereas the label did not have that tree. Okay, it's tough to label these huge images, so you may find that your model is performing much better even though you're getting 80% IOU, 85% IOU. Maybe that's because you're picking up things that are mislabeled in the original testing label. If they have done a great job, then of course you can rely on that. So these right there, we are getting pretty good segmentation, yeah, right there. And same thing here. So the label did not show anything like for this area, but I do see a tree right there. So I'm not surprised that my model is showing a tree right here, okay, in my segmented image. So this is a start right there. Again, here someone used a polygon tool to kind of label these trees, but in reality they are not polygon, they are like rounded right there, and we are doing a good job right here. Okay, so this is a quick preview of what you can expect if you follow this on this specific data set. Okay, now let's go ahead and jump into the code and address this in a methodical way. I'll try to go as fast as I can, but not fast enough to miss any information, okay? Which means this is going to be a relatively long video. Okay, let's jump in. Okay, just a quick look at the data set. So just go ahead and type landcover.ai and you'll find, you'll land onto a page that looks similar to what you're seeing on the screen. Go down and go ahead and download the data set right there, okay? And it would be landcover.ai.zip. And when you unzip that, it is going to give you, let's go into data, images and masks, okay? These two, that's it. And split, readme, test. So anything from here to, images, masks, these are the ones you're going to see. I completely ignored everything, even the split part. I mean, if you want, you can go ahead and look at it. I just look at images and masks, and then I come up with a strategy of my own. So if you want to look at the images, again, these are all like different size images. You see, this is 53 megabytes. If you look at this, this is probably 9K, yeah, 9 by 9K. Very large images, right? You cannot fit these in the memory and start training, right? At this, most of you cannot, especially if you're using GPU. Okay, so these are images, and then all in TIFF file, and you have corresponding masks also in TIFF file, okay? And just because I'm showing you this, they all look black. And a most common comment that I get as part of this channel is, hey, I segmented my images, I followed everything you mentioned, but my images look black. Well, they look black because you're using Windows to visualize the image. Just go ahead and use a scientific, open them in Python, for example, and use matplotlib, or just use ImageJ, or some other scientific imaging program that can let you change the image range. What I mean, open the image, adjust the brightness and contrast, set this to 0 to 0, 1, 2, 3, right? We have 4 classes. So let's just go to 0 to 3, adjust it. There you go. And let's set this to 0 to 4 and see, is it 0 to 4? No, it's 0 to 3. That's fine. So now if I hover my mouse over, you see up here on the panel right there, you'll see a value of 0 or 1 or 2. You see right now it says 0. That means that area is not annotated. Let me move this slightly to the right. Now the value is 2. This is all Woodlands, I guess. Now if I go down here, that looks like houses or something, the values will be right there. You see the value is 1. Okay, I don't know if there is any water here, but that would be a value of 4. So again, I'm spending a bit of time trying to explain the data set because obviously it is important to find out or to understand what you're trying to solve. Okay, so images and masks. The next step, what I've done, let's open the code. So I started with that. Then I thought, okay, first step, I need to break down those images into smaller patches of 256 by 256. If you have smaller memory, try 128 by 128. I try not to go any smaller than 128 because if you chop them into much smaller images, you lose the context. If there is part of the house here, part of the house there, you lose that. You get like misclassification if you have these on the edges or even in the center. If you don't have like a good context, yeah, then you may get some misclassification. So try not to chop them too small. To me, 128 is as small as I go. 256 is okay. In fact, if you want to compromise on the batch size. Only do 4 instead of 16. Okay, another tip right there. So first, I create a file. I'm going to share all of this with you. So please pay attention to the video for now. Here, I'm preparing the data. What do I mean by preparing? So this part of the code achieves 3 tasks. 1, it reads the large images and the masks that we just saw, divides them into smaller patches, each 256, or you can define your size. That's the first task, and saves to the local drive. Okay. And the second part is save only the images and masks where masks have some decent amount of label, because I realized that these images are so large. When you cut them down into 256 by 256 patches, most of the patches, almost half of the patches, they do not have any labels. The only label they have is 0, which is unlabeled. So why do I waste all my computing time training on those patches? So I just eliminate them, right? So don't use them. So that's step 2. Step 3 is divide this sorted data, right? The data that I just have after eliminating the ones that don't matter, divide that into training and validation, right? We need training and validation data sets. And finally, move the folders in a way that our Keras image datagen can understand. So let's go through the code. I'll highlight the piece. I copy these libraries from one file to the other, so most of these are probably useless. I'm not using tip file, for example. I'm not using this. I'm not using this. So just ignore these. I'll import them anyway because we'll need them in a different file. But for now, let's go ahead and import these. Okay. Next, I'm reading one file, just one single file, just to get a good understanding of what's going on. So let's do this part for now. So temp image is I'm using OpenCV to read this TIFF file. This is just my input image, right? So this is 9.2K by 8.9K by 3 channels, okay? I think these are 3 different bands. The 3 channels indicate 3 different bands in this image. And now let's go ahead and have a look at this. Band number 0, like each channel, right? I'm visualizing each band right now. So there you go. So that's band number 0. And next comes band number 1, which should look similar, but depends on what band they have used. There you go. Slightly brighter, certain areas highlighted, and band number 2. Again, this is a typical exercise you go through, right? You want to get a good understanding of how the images look like. Band 0, band 1, band 2. Okay. Next comes my mask. Let's do exactly the same for the mask. I'm reading my mask. Again, it's a TIFF file, so I'm using exactly the same way. And now I'm trying to, instead of visualizing it, let's go ahead and print out how many labels and how many counts per label that I have. So let's go ahead and run that. You know that np.unique gives you the unique values in a given array, and if you return the counts, it's going to tell you how many. Okay, so that's exactly what I'm going to do. Go ahead and print out. So what do we have here? So we have labels 0, 1, 2, and 3, right? These are all 8-bit images, so they go from 0 to 255, the values. The labels actual data is 0, 1, 2, 3. No wonder they look black, right? Because my bright is 255. Anyway, so I have how many ever? This is 26 million pixels corresponding to 0. These are all unused. I mean, these are all useless ones, remember. And we have these many real pixels. Okay, so that gives you a good understanding of what's going on. And the next part is where we divide these images into patches. Okay, so I'm defining what my root directory is and what the patch size, my desired patch size is. So I'm dividing them into 256 patches. And the rest of the part, we have used this in many of my videos to read images. So I'll go through this a bit fast. So this is my root directory, and I'm walking through each file in my root directory. Only the files ending with TIFF. Yeah, in my case, they're all ending with TIFF. And then I'm using OpenCV to read it just exactly the way we have done up here. Yeah, so at this point, I have a very large image. Then I'm going to calculate the nearest size that I can crop it to. Okay, if you look at this, what do I mean by that? If you look at this image, 9289 by 8914, if I divide this into 256 patches, I may have some pixels left over. It's tough to take care of these remaining pixels. I'd rather ignore those remaining pixels. Okay. Of course, you can come up with a plan of, okay, if you have like 5 pixels overlapping between your patches, then you can cover this, all of that. If you're smart enough to do that, go ahead and do that. For me, I have enough images anyway. I don't care if I lose a few pixels here and there. So what I'm doing is I'm cropping this image into a size that's near enough to be divisible by 256. Okay, so for the sake of fun, let's go ahead and do up to that point. Yeah, root directory, sorry. Let's do these 2 lines because I just want to show you what the result would look like. So let's do that, and let's go ahead and read the image. Image name is not defined. Let's go ahead and print the image name so it does something first. Okay, and then you see for each of these images I'm going to do the following steps. What is the following steps? First, read the image. If you look at it, my image right here is 4672 by 4230 by 3, the first image. And then I'm going to figure out what the size in X is and size in Y is that's divisible by my patch size, which is 256. So if you look at that, my size in X is 4096 and size in Y is 4608. These 2 numbers are divisible by 256. Why do I care about that? The next step is I'm converting that into a pillow image and then crop the image. So I'm taking my large image and cropping it. Okay, and you can crop from the center. I'm cropping from top left. Crop the image and then save it back to a NumPy array. Now I have a large image that's divisible by 256. Okay, and the next step from this point on, I'm using a library called Patchify. Okay, go ahead and pip install Patchify if I haven't written here. This is the library I'm using. Go ahead and pip install Patchify, amazing library to divide your images into patches, whether the images are 2D or 3D. Okay, so I'm dividing my images into patches of 256 by 256 by 3 and then move 256 pixels. So no overlap between images. Okay, you can do overlap if you want. So I'm not overlapping, I'm just dividing the images. For training, this is fine. Okay, so do that. And then capture all of that into a NumPy array. That's exactly what we need to do. But if you are training using a stored NumPy array, but we don't have that type of memory because that would be 40,000 images or something. We don't have that type of memory. So I'm going to save the images to my local directory. That's exactly what I've done. Now let me open. Oh, by the way, I have done exactly the same for my masks. Same operation for my mask. Okay, exactly the same. So my masks and images line up. So that's what I have done. So initially we started off with images and masks. Now I have 256 patches and I divided them into images, and you see I have 41,646 images when I divide these large images into 256 patches. And of course, corresponding masks, you'll see all of them as black for the reasons I mentioned earlier. Okay. Okay, now next what? Next step. Well, you can plot them if you want and have a quick look at it to make sure everything matches up. The next step here is let's copy images and masks with real information to a new folder, meaning anything that has whatever significant amount of information, let's copy them into a new folder. Okay, so I'm going through these 2 folders like my masks and images and identifying all the images that have real information like not unlabeled and copying them into a new folder called images with useful info / images and masks, right? So I'm pasting them into this directory where I also have images and mask subdirectory. Okay, obviously putting images here, masks there. Now what is the criteria? I'm actually looking at, remember the np.unique we just looked at? It tells you what are the unique pixels and how many of them. I'm using that information. So in each mask, load an image and mask and only look at the mask and find out how many counts and what are the pixel values and how many of them. If counts 0, which is the 0th pixel, unlabeled pixels, okay? If the fraction of unlabeled pixels to the total number of counts is more than 95%, or in other words, if 1 minus that is greater than 5%, then save it. Then say save me and then save both the image and the mask. If not, I'm useless. Go ahead and continue. Okay. Again, don't want to confuse you. All I'm doing is I have 40,000, 41,000 images. I know that bulk of them are useless. So I'm just setting a criteria that if the real annotations, that means if the value is not 0, it's either 1, 2, 3, okay, then greater than 5% of the image, then save it. That's all I'm trying to do here. Okay, so that's exactly what we did. We ended up with 20,000 images here. Okay, again, there are many ways. This is the preferred way. This is the way I came up with, just looking at this and not knowing anything, just looking at the data. Okay, and let's move on to the next one. Next step is split the folder into train, test, and validation, right? So now we have a folder that has images and masks. I'm good. 20,000 images, 20,000 masks. Now what? I want to divide this into training and validation, just randomly picking subset of these images. So for that, a great library is split folders. Yeah, pip install split dash folders, and then import split folders, give it the input folder, the output folder, and then the ratio. Here I divided them into 75% training, 25% validation. You can also give a third argument right there, in which case it divides them into training, validation, and testing. Okay, so those three. So for now, split this into these, and that's exactly what it did. If I go back and look at data for training and testing, right? So this is where I saved, yeah, data for training and testing. So you see how it creates two directories, train and val. Under train, I have images and masks, how many ever, 15,000, obviously 75% of 20,000, yeah, 15 right there. And then masks, same thing. And then if I go to val, you should have about 5,000 images here, 5,000, this is my val, okay? Normally this would be good if you're doing classification type of applications, because if you're using image flow from directory in Keras, then there needs to be a specific structure. And we are trying to trick the system into thinking that this is classification, but then we are using the same for semantic segmentation. If that doesn't make sense, just blindly follow this. If you are trying to use flow from directory in Keras, the structure that you need to put your data into for semantic segmentation, yeah, I'm not talking about classification. For semantic segmentation, in classification, you have training, you have validation. Under training, you have different folders, and each folder corresponds to a specific class, correct? For semantic segmentation, you have train and you have val. But under train, I have images with my images, and I have masks with my masks. This is my current directory structure. I have to spend some time here, sorry. So under my data, I have train and val. Under train, I have images, masks, right? Under train, I have images, masks, and each one of these contains images. But it needs to be in the following structure. So I copy my images, this folder, into a new structure. I renamed it as train images. That's it. So let me just show you what I have. Data for Keras augmentation. This is what I have, okay? I divided this into train images, train masks, val images, val masks, and subdirectory train here. Even for masks, subdirectory should be train. Okay, so train images, train masks, train, and then val images, val masks, val. Okay, this is the type of structure that you need to have if you want to use flow from directory for semantic segmentation. Okay, now we are really done with pre-processing. We have everything that we need here in the structure, in the order that we want. So the next step is, let's move on to the next step right there, training. Now we are ready to do the training part, okay? Let's go through this again step by step. So first of all, I'm going to use segmentation models library, the unit from that library. You can use any unit, it doesn't matter. I wanted to test with some pre-trained backbones like ResNet backbone with ImageNet weights. That's why I'm using segmentation models library. If you end up using that, you will probably run into on Python 3, you will run into an issue, an error message that says generic utilities error. I already talked about this as part of my Python tips and tricks video. Go ahead and watch that video to fix it, okay? Or you have to roll back your TensorFlow to 1.4 or something, yeah? But this is an easy fix, very quick fix, okay? Now, let's move down. So let's go ahead, clean everything that we have done until now to make sure we start with a clean slate. Let's also clean the images. Okay, so now I have my images ready. The next step is import the libraries. Again, these are all pretty standard except for the segmentation models that I just mentioned about. The next step, get an understanding by look at a few. Sorry, I keep try to skip these in the interest of time, but just to make sure, if you ever run into when you're running your model.fit And then when you see, okay, epoch number 1, it takes like, I don't know, 1 minute. Epoch number 2, it takes 1.5 minutes. And then it keeps increasing. At some point, it gets so bulky, it's going very slow. If you run into that problem, check out these 2 links to fix it. Okay, in this case, I am not, but initially when I was trying something else, I did run into that, and you can check these 2. I'm going to share the file, so don't worry about it for now. Okay. First, let's get a quick understanding of the data, because we may be sorting our data, today and trying to do the training part 1 month from now. So we don't know anything, right? So we have to start from understanding the data. Okay, how do we start? Let's go ahead and define our directories. Remember, we saved everything into data for keras org right here. Okay, so that's exactly what I'm doing. Train image directory is data for keras org, train images, and then train masks is for mask directory. So let's go ahead and define those 2, and then also define the next 2, which is basically using the OS library to list all the images within that directory, right? I mean, that's what os.list does. If you look up here, it's just the image names. Why am I doing that? So I can kind of load images. That's it. Now let me go ahead and create a random number generator right there. Where is it? Image. Oh, sorry, I did not run this line. So number of images is my length right there, which is 15,056. Okay, my number of images is 15,000. So now let's generate a random number between 0 to that number, and then load a random image, okay, from that directory. So from that list, I'm loading a random image, and I'm converting that image from BGR to RGB. Why? Because we want our grass to look green, and reds and blues at the right place. Yeah, so OpenCV reads images as BGR, so I want to convert that to RGB for visualization purposes only. Okay, and then I'm reading the mask at the same time. So let's go ahead and plot the image and mask. Why am I doing this? Again, we have done a lot of operations. We took large images, we cropped them, and then we saved them. We saved images and masks. I get paranoid. Are they actually lining up when I read the images and masks? Because I don't want to spend a lot of time training on wrong data. Okay, so let's run these image number. Yeah, from here, just to see a couple of images, and hopefully they should line up. There you go. That lines up pretty good. My green and unlabeled area. There you go. The greenery is right there. There's so much greenery, very few data about real images, so it's tough to see. There you go. Water and land. And yeah, I think that proves the point. Yeah, there you go. Yeah, houses. Okay, everything seems to be lined up. Sanity check. Let's move on to the next one. Let's define the generator for images and masks. I did a Python tips and tricks video a few weeks ago on this topic, where I showed, hey, if you want to use image generator, but then if you would like to pre-process your images or convert your masks into categorical, how to do that. Okay, you can watch that video. I'll cover that in a second. Right here. So let's go ahead and define a seed. So we use the same seed for both our images and masks, so we can read the same images when we're using the data generator. And then let's load 16 images at a time. If you're low on memory, try 8 images or even 4 images. Okay, but I try not to compromise on the image size itself. And here we have 4 classes: 0, 1, 2, 3. So let's go ahead and do those. And the next thing is, I do not want to divide my images by 255. I want to instead do min-max scalar. So I'm defining that. And then let's import to categorical so we can convert our images to categorical. So in segmentation models, you can get your unit with different encoders. So here I'm going to use ResNet34 encoder with pre-trained weights of ImageNet. That speeds up our training, by the way. That's the reason I'm using pre-trained weights. So because I'm going to use ResNet34, I need to pre-process my data exactly the way they have pre-processed before. And the way you do that with segmentation models library is sm.get preprocessing, okay, using that backbone. So let's run these 2. We need to apply this object onto our images, but I'm defining that right here. Okay, so now comes a function that preprocesses data, that takes image, mask, and number of classes and converts my image. First of all, using min-max scalar, applies the min-max scalar, and then preprocesses this using what I have defined here, and it converts my masks into categorical. Okay, so this is my preprocessed data function that I'm going to call, that I'm going to apply onto every image that my data generator is going to generate. Okay, so down here is my actual data generator from Keras, and this part I hope you are familiar with. Again, no tricks here. I'm importing our image data generator from Keras, and then defining a function that takes in the training image path, training mask path, and number of classes. To do what? Well, image data generator, horizontal flip and vertical flip. Okay, so it's doing is horizontal and vertical flip. I'm not doing any zoom in, any rotations or anything, because for semantic segmentation, I do not want my mask pixel values to change. I want those to be 0, 1, 2, 3. That's it. When you do these rotation zoom in operations, you have to fill in the intermediate pixels with something, right? So usually most of these approaches, fill in those using some sort of an interpolation method. I don't want that. I have enough images anyway, so I don't want to generate or new type of images. So let's go ahead and only use horizontal and vertical flip. I'm going to define both image and mask data gens using that. Okay, next comes basically flow from directory. We talked about this flow from directory. What is the directory? This is my training image path. Okay, and no class mode, because we are not doing classification type of application. So I'm going to say no class mode, and batch size is 16 in this case, and seed equals to seed. This is very important. You have to set exactly the same seed for both mask and images. Okay, in addition, I'm reading my masks as grayscale. That's the only difference, because they're all grayscale. So let's run. Oh, by the way, the important part I'm skipping. So here you have your image generator and mask generator, right? So I'm zipping them together. So when I call train generator, it gives me both image and mask generator. Okay, now let's go ahead and apply the preprocess function we defined here, that actually scales images, pre-processes images, and then converts my masks into categorical. That's exactly what I'm doing here. For each image and mask in the train generator, right? I get 16 images at a time. For each of these images, go ahead and pre-process the data. We just defined the function. So that's what this is doing. And yield means it's giving me that batch number of images at a time. And then wait. And when I say next, go ahead and give me the next batch. Next batch. Okay, so that's exactly what's happening here. So let's go ahead and did I run these lines? No, I did not run those lines. So let's go ahead and do this. Okay, now slowly getting there. Let's go ahead and define the train image path and train mask path. Okay, and then my train generator. You know that the train generator takes 3 arguments: the image path, mask path, and number of classes. So this is my train. I did the same for validation. So this part is pretty straightforward. So once I do that, now my generators are ready. I can go ahead and train it, but I want to visualize the data. How do you do that? Well, whenever you have a generator that's yielding you images, you can walk through the images by using the next command right there. So if you're using Python 2 point something, then it is just next. If you're using Python 3 and later, it's _ next, this one. Yeah. So let's go ahead and define that. And if I go to my variable explorer, nothing right there. And if I run this line, we should see X and Y in a second. There you go. And it found 15,056 images in each of these folders. And my X, 16 images. Each image 256 by 256 by 3, and my Y, which is the mask, right? The second output that the image generator is giving me is the mask. Same 16 images, 256 by 256 by 4. Why 4? Because this is converted to categorical. Yeah, and we have 4 classes, so that's why 4. So we know the data is ready to be trained on. So let's go ahead and plot and I'm plotting only 3 plots at a time. So let's plot these and have a look at it. So there you go, these 3 plots. Okay, so they're looking good. Let's do one more. Let's walk one more time and then plot these. We should get 3 different images now. So there you go. They haven't labeled the roads or anything. Yeah, so houses, grasslands, water, and unlabeled. Obviously this is unlabeled. Okay, so that's doing good. I did exactly the same even for validation, just to make sure if your validation makes sense. Yeah, so again, it says 5,000 images belonging to one class, which makes sense. Okay, Now let's come to the serious part of this. The data handling part is actually the serious part. This is the fun part. Now it's easy, okay? Defining the model. So first of all, let's define number of training images. We know that this is 15,000 something. I am assigning that to a variable. Same with number of validation images. Why? So I can define my steps per epoch, which is basically my total number of images divided by batch size, okay? That way we ensure that every image gets through each epoch, okay, through our model. Same with validation. Let's go ahead and do validation steps per epoch, okay? So if you're curious, my steps per epoch right now is 941, okay? That many iterations to go through all my 15,000 images. Basically 941 multiplied by 16 is our batch size, will give you about 15,000 images, okay? Now let's define our image height and image channels and number of classes. Why? Because the model we are going to import requires those as input. So from segmentation models, I'm going to import unit model. You can define your own unit. It works with your unit also, of course. I'm going to use the backbone, which we already defined as ResNet, and use ImageNet weights for the encoder part. And then my input shape is the one that I just defined. And my total number of classes is 4. Do not forget to add activation softmax because this is multi-class semantic segmentation. So you need softmax. And then I'm going to compile the model using Adam as optimizer and categorical focal Jacquard loss. These losses are available as part of your segmentation models library. Go to the documentation and see all the losses that they have. They only have focal loss. They only have Jacquard loss. Jacquard is like intersection over union. And this is basically categorical focal Jacquard loss is focal plus Jacquard. That's it. Okay. And for the metrics, I'm going to track intersection over union score. Okay. So those are the metrics. So let's go ahead and run those lines and print out the model summary if you want. Let it do its thing over there, and then let's go ahead and print out the summary. Don't worry, I'm not going to train right now. I have already trained it. So let's go ahead and print out the summary. You see the final, it's giving me 256 by 256 by 4. Let's just print out the input shape just to make sure we are not messing anything up. 256 by 256 by 3. That's great. Now you can go ahead and train the model. In fact, looks like I trained it only for 25 epochs in the interest of time, and it already did a good job. Okay, so next step, you can go ahead and plot the training and validation curves. But now let's come down here, load the model that we already trained, and check things out. Okay, so I'm loading the model. Again, I put compile equals to false because we just want the model to for testing purposes and not for training purposes. Okay, so there you go. And now comes testing and applying this onto some of the images. So let's use validation image generator to generate a batch of 16 images and masks, and then just go ahead and predict on these and plot them, or at least get IOU value. That's exactly what we are doing around here. Let's see what the mean IOU is for this batch of images. Okay, for the different batch, it may be slightly different, but on average, this gives us a good idea of whether our model is performing well or not. Okay, so this is still working. While it's working, well, let's finish it off by, okay, once it's done predicting, we are just going to view a few images. Okay, so my mean IOU for this set is about 79. That's not bad, 79%. And let's go ahead and visualize some of these images. Okay, so randomly load an image. Okay, nothing to see there, not much. Yeah, that's not bad. In fact, I like the way my model predicted. Here they used a polygon tool, so you don't get the rounded edges clearly. So there you go. I can't even see what's going on. I mean, we got, let's see. Yeah, right there. This area is okay. Even this one right here, they don't have it, but there's a tree right there, right? I mean, we are picking that up much better. Water, it's picking up very good. And the other region, it's also doing a great job. So we can stare at these forever, but let's move on to the next step, which is, okay, now we know we have a model that's working fine. Apply this model to a large image. How do we do that? Okay. I did a video on this smooth tiled prediction in the past, so I am going to use the library that's created by these guys, but that library has some error. 4 years ago, not much happened in the past 4 years, but this is designed to take your large image, and we are going to apply our model saying, okay, I want to apply that on 256 by 256. It's going to divide your image into 256 by 256 patches, apply it, and then smoothly blend it. Here you see, if it's not smoothly blended, you see the edges right there, all 256 checkered. You see your image looks checkered. With smooth blending, it looks more continuous. So it has a couple of errors. In fact, if you go to issues up here, I did post, if I open, I think one of these, a couple of these, I did post a fix right there. Yeah, this is my response right here. I did all of that in this piece of code right here. Okay, so this piece of code should work right away. So it has basically a way of smoothly blending images. That's it. So we'll be calling that, where is that function? We'll be calling predict image with smooth windowing. We'll be calling this function by providing the input image, the window size, like 256 in our case, and the predict function, basically predict, model.predict. That's it. Okay, so now let's get into our code that I think you'll find easy to understand. So all we are doing is, again, loading the required libraries, and this code is very small, by the way. This is not much. Okay, again, you probably don't even need these two, but load these and min-max scalar. Why? Because we have to pre-process our images exactly the way that we processed our images during training, right? So that's why I have my min-max scalar right here, and that's why I also have pre-process input, right? These are the two things that we have done for training. And in addition, I'm importing this predict image with smooth windowing, which I just showed you, that function from this file. And that function, I'm going to apply that down here. Yeah, this is that function. So the next step, load the large image. This is my large image. Okay, and then apply min-max scalar, right? This one, we have to do that, and then pre-process. This is exactly the steps. Again, yeah, let's go back, because I really want to make sure everyone's on the same page. You see, min-max scalar, pre-process input, that's exactly what we have done to our images during the training process. So during the prediction, I'm doing the same. Okay, for my mask, there's not much. I'm just looking at the 0th channel for my mask, and I'm loading the model, right? The model that we trained, 25 epochs, ResNet backbone, batch of 16. This is the model we just saved after training. Okay, I'm loading that, and I'm defining my patch size as 256, number of classes as 4. That's it. Once you define these, now I can predict on my large image. Using this function, on my image, my window size is my patch size, which is 256, and number of subdivisions is 2. Number of subdivisions is a weird way of saying overlap. When I say number of subdivisions equals to 2, I believe it's actually taking 256 image, another 256, and overlaying them like halfway through. So you have a nice overlap. You can do number of subdivisions as 4 and see how that works out. I think the higher it is, the slower the prediction is going to be, because you're predicting the same area multiple times, right? In the patches. So that's the number of subdivision. Number of classes is 4 in our class, and the prediction function is basically a lambda function. For each subdivision, it's going to do model.predict. That's it. Okay. So when you do that, your final prediction image is right there, and then your final predicted image is a one hot encoded image. So you need to argmax to get the pixel value 0, 1, 2, or 3. That's what I'm doing here, and then I saved both of these images, and you can plot it. Let me go ahead, and where did I save? Data test images, test images right there. So there you go. So this is C43. Looks like this is the last one that I did, but there you go. So this is the original image. This is the the mask, and this is the segmented, what we get from our segmentation. Okay, so very nice segmentation, as you can see. This is the another test image with a different, there's water going on here, there's water right here, and you see the segmentation is pretty good, actually. Yeah. And they are smooth. You don't see this to be tiled or anything. That's the most important part. Okay, so as expected, I should say, not anticipated, as expected, this turned out to be a rather long video, about 45 minutes or something. But any of you guys who are interested in satellite segmentation, this hopefully provides a framework that you can work with, right? I mean, you often deal with large images, multi-band images, and you need to cut them down into smaller images, and you need to make sure you're not wasting the computing time by not using the images that do not contain much of any information, and use only the ones that have maximal information, and then use image data generator to load them from the disk. And when you load them, okay, it's giving you batches of images and masks, but then you take that batch and apply additional operations if you would like to. In this case, because this is multi-channel, go ahead and convert them into categorical, and then scale your images, pre-process your images, and then you have your data ready for training. The training part is very simple, 2 lines of code, right? The training part is easy. And once you save the model, go ahead and use this smooth tile predictions library. Thanks to these guys, go ahead and use them to predict on your large images. If you're not working on satellite images, if you're working on something else, exactly the same thing, right? If you're working with large images, this can be a great framework to work with. Okay, again, thanks for sticking up to the last point, guys. And I know now that you spent 45 minutes, you love this video. So go ahead and hit the subscribe button and also hit the like button, okay? Because I know you like the video, okay? Thank you, guys. Let's meet again in the next video.